Welcome to the Ultralight Airplane Workshop. My name is Leon. Let's figure out the wing planform for the UWS-1 Ultralight. This is part 2 of a two-part series determining the planform for the UWS-1 Ultralight Airplane. First part evaluated various planforms that we found in Horner's Fluid Dynamic Lift book. We looked at the elliptical, rectangular, and triangular planforms. Let's use what we learned from Horner to come up with the planform for our new ultralight, and let's use the OpenVSPAero program to do some analysis on it. You may recognize this page from Horner's book on fluid dynamic lift from our previous video. This diagram is showing the load distribution and coefficient of lift distribution for 3 different wing planforms. What I would like to do in this video is to try to reproduce this lift distribution and coefficient of lift diagram using a program called OpenVSP. OpenVSP is a program that was initially designed to allow you to rapidly configure an airplane, the geometric configuration of it. Not too long ago, they added another capability is to do a little bit of computational analysis on the configuration, in particular wing and horizontal tail and vertical tail configurations. So what I would like to do is configure a few of these planforms and then run some analysis on them and see if we can duplicate these diagrams. You can find OpenVSP online by just doing a simple Google search on OpenVSP, Victor Sierra Papa. So we get started by adding a wing. This is the default wing OpenVSP puts in whenever you add a new wing. I can scroll in and out on this a little bit by holding down the control key and then moving my mouse up and down. We'd like to have that rectangular wing. So we're going to have to do a couple things to fix this. We have to get rid of the sweep, and we have to make the root the same size as the tip. Let's go to our plan, and let's set our span to 30 feet, because that's what I've been using for our design so far. Oops, I believe I made a mistake. That was 3.0. 30.0. There we go. There's 30 feet span. I happen to know that my chord is 3.6 from some previous calculations we've done in a previous video. Now, we need to go to the section. Section works on one section of the wing. And the wing has been set up to mirror from one left side to the right side, or right side to left side, whichever you like to think about it. So now we're only working on one half of the wing. We want to get rid of the sweep. So we can come up here and we can say 0. Now this is setting the sweep to 0 at the leading edge, and that'll be fine since we're going to set both the root and chord to the same length. If we were doing a tapered wing, we would set the location for where we are determining the sweep to be the 25% chord. So we would add or set this to 0.25. And now you can see it's 25% chord that has 0 sweep. Let's set our tip and our root to the same size. We'll do that by setting our taper to 1, which means both the root and the tip have the same size. Now it changed this root chord, so let's go set it back to 3.6. One thing to mention here is now that the root chord and the tip chord are now both set to the same length, it doesn't really matter where we set the sweep location. It can be at 25%, 0%, and by the way, percent is from the leading edge of the wing. So 0 would be leading edge, 1 would be trailing edge. At 25%, roughly this location here. Doesn't matter where we set that. The sweep value would affect the whole wing the same, trailing edge, leading edge, and in between. That should be our wing. Just verify. Let's go back and see what our plan is. Our plan says our 108 square feet, which we got from our previous videos. Span is still 30, and our average chord is still 3.6. So now we have a nice rectangular wing. Before we go and do our analysis on this, we need to, let's zoom out just a little bit. There we go. When it goes to do analysis, it cuts the wing up into panels. And it's going to use these panels, or we're going to tell it to use these panels that we have here. There's only, 5 panels across the section. and it's pretty crude out here at the tip. You want to have a higher density of panels where you know you've got significant changes in the way the wing's operating. So here near in the middle, and not only in the middle of the chord, but in the middle of the wing, there's not going to be significant changes. We will have changes at the edges, leading and trailing edges, because that's where you have air coming in and suddenly separating, and the air coming back together, trailing the edge, and you've got tip losses. So we're going to change what's called the tessellation of the wing. We're going to add some more tessellation so we get a little bit finer detail across the span. So we go to our section, and we're going to increase from 6, now 6 means the number of lines across here. We're going to crank that up, and we're going to go up to, let's try 10. I think that should be sufficient. I would like to have them be a little more dense here at the tip, so we'll do the tip clustering, and we will slide that down, and you will see that these tessellation lines are starting to get more dense out at the tip. That's not too bad. I think we can live with that. Yeah, I believe that'll give us reasonably good results. So we are going to try this for our calculations. Another thing to show on this is we can do some interesting things like rotating our wing around, and if we zoom in here on this tip, you can see we have a pretty symmetric airfoil, and the tip, I will make it so we can come out here and see the tip a little bit. It's kind of hard to tell, but the tip is flat here on the end. And that's fine. That's kind of matches what we really want to do for our calculations. And to get to a nice view, we can come up here and say View Top, and it'll come back to the top. But we need to zoom back out just a little bit. There we go. Another thing to do is, you notice that was symmetrical airfoil, and we're going to stick with that for now. But what is that airfoil? Just in case you're curious, we can come over here and click on the airfoil tab, and you can see it is a NACA 0010 airfoil. So that's a 10% NACA 4 series airfoil. It has zero camber. The camber location is at 20%. This really doesn't have a significant impact on the calculation that we're going to use though. Now we come to the part where we're going to do a little computational analysis on our rectangular wing. First, I want to save out this wing, so if we have a little screw up, we can come back and work on it some more. I'm going to store it in this rectangular file. Alright, now we come underneath the analysis, and we come down to VSPAero. We're going to use the vortex lattice method. We could use the panel method, but it does not give us lift information. I'm not going to get into the differences between the vortex lattice method and the panel method. There are some pretty good Wikipedia articles on both of these. You can just do a quick Google search on vortex lattice method and on panel method, and you can find out what the differences between them are. So for now, we'll stick with vortex lattice. We're going to tell it to get a reference area and lengths from the model. So you can see we now have our 108 surface area, our span of 30, and our chord of 3.6. We're not going to do any moment calculation, so this doesn't really matter, but we can go ahead and do a calculation here. Over here on flow conditions, I think this will be okay. We've got a start angle of attack of 1 degree, it finishes at 10, and increments of 3. We're not going to have any side slip, so our beta angle is 0. So I'm going to pick a cruise speed of 55 knots that we will do these calculations at. And a Mach at 55 knots cruise speed is 0.083 Mach. Let's launch our solver. It's going off and doing some calculations back here so we can see it moving, and it's come up with our information. We are looking at coefficient of lift multiplied by the local chord divided by the average chord. So this is going to give us a distribution of lift across the wingspan. So here's the center of the wingspan, and here it is coming across. We have 3 lines on this screen because back in the specifications for VSPAero, we said we wanted 3 different angles of attack measured, starting at 1 degree, going up to 10 degrees, So since we asked for 3, there will also be one right square in the middle at 5.5. So this is an angle of attack at 5.5 degrees. This is an angle of attack at 1 degree, and this is at 10 degrees. This isn't quite as flat in the middle as we saw in Horner. Let me bring that up real quick. Here is the lift distribution for a rectangular wing, and it's fairly flat here and comes out and drops quite a bit. It's not quite what we're seeing here. You can see that it is not too far off. There's another thing we can do is just look at the coefficient of lift by itself. Now as you can see, there was no difference. So I click between the distribution and coefficient of lift. There is no difference. And that's what we saw pretty much over here at Horner also. These two are very similar. Now let's save this out. VLM. We're done with this analysis for now. Well, now let's play around with the triangular planform. Now, just to save you the anguish of watching me go through and struggle through setting this up, I've gone ahead and done it ahead of time, and we'll just go over real quickly what I did. One of the issues that our lattice solver has is that you can't have a 0 chord wingtip. It'll crash the solver. I believe that's because there's a divide by 0 error. But we can make it very small and still have it work. What I've done then is I've gone in to the section for the wing and I set the wingtip to 0.1 feet. So it's pretty small, just a little bit over an inch. And the root is 7.1, so that gives us our average chord of 3.6. And so we still have our wing area of 108, our chord of 3.6. So we're still keeping that the same, and our span is still 30 feet. I've also done the same number of sections for the semi-wingspan, which is 10. And I've also clustered at the tip a little bit more so we get better resolution on our tip when we go to do our computational analysis. Now that we have that done, let's go ahead and run our analysis. So we run VSPAero. And we've got our information from the model. We're running the vortex lattice. We have our Mach number of 0.8. We're going to do those 3 different angle of attacks, starting at 1 degree, finishing at 10. So we are ready to launch our solver. Okay, and there it is. Now this is our lift distribution, which is somewhat similar to what Horner had. Let's come over and look at that real quick. So here's lift distribution. It's kind of parabolic. So let's go back and look at what we actually got. There is some similar to a parabolic shape, so that's interesting. Good. So that's the lift distribution. Now let's look at our coefficient of lift. Aha! So now we have a significant increase as we get out to the tips, especially at this very high angle attack. When we're at a low angle attack, this one is the 1 degree. It's still increasing the whole distance. This is our 4 degree. And this is our 10 degree. So let's look at Horner again real quick. And look at what his coefficient of lift. So we are seeing something very similar to that. So we're verifying that through this computational analysis. So that's interesting. I want to save that out so we can come back to that later if we need to. And we'll put that down in our data directory. The only thing left to do is to try to do the elliptical shape wing. And that's going to be difficult to do. Again, we can't set our tip to a 0 chord. So we're going to have to massage things a little bit. I'll go through and set that up, and then I'll come back and talk about what I did in order to set it up. Well, I've created an elliptical planform for a wing here in OpenVSP. It's a lot more difficult than the square or tapered or mostly triangular wing. Making these curved edges, this is the trailing edge and this is the leading edge. Here is the root. Making these curved edges was quite a challenge. I bring up the geometry setter for the wing here. I've still got the 30-foot wingspan, and I've got 109 square feet, so I'm only 1 square foot above the 108 I've been wanting to use. The average chord is now around 2.45 feet. So that's a little bit less than the 3.6 we did have for the rectangular wing. What I had to do for this is I would cut this up into many sections. And let me show you that real quick. We're seeing one section there, but I'll come back to the first half section. The OpenVSP is responding a little bit slow at the moment. I haven't figured out why that is. So I've cut up the inboard half into one section, and then what I did is I took the outboard half and cut it in half. So that would mean there's 2/4 out here, and then I cut that in half. And I just kept cutting it in half as it went farther and farther out. And these last two sections are the same size, but they're pretty small. And then what I did is I went into the spreadsheet and calculated what the chord would be at each of these stations. And then I went in and set that chord length, keeping the 25% chord as a straight line. And then I went into this blending mode. And what I did was I set the angle at each of these stations, and then it went and did the curve for me in between each of these stations. And I still have a 0.1 chord length out here at the tip, so it doesn't come down to 0, otherwise we'll get our little error. So that's what I did to create this elliptical planform. It was not easy, it took quite a bit of work, but we got her done. Now let's do some analysis on this planform and see if it matches what we got from Horner's book. I've already done this once, so most of this is already set up. We're still doing the 3 angles of attack. Our Mach number is 0.08, which is 55 knots, or close to it. We use our model to come up with the wing geometry, and we launch the solver. All right, what we're looking at here is the load distribution. So this is at the 1-degree angle. This one's at the 10-degree angle. This is in between. So let's go back and look at Horner real quick. And for the elliptical distribution, our load distribution it's hard to tell if it's elliptical or not. It kind of resembles it. It also kind of resembles this parabola, so it's difficult to tell if we really have an elliptical distribution. We would have to do a fit to see how close it comes to elliptical, and that's one thing I'd like to do here before too long. Now remember that on the coefficient of lift distribution is pretty much flat all the way across. So let's see what that looks like. And that will be this little symbol here. And it's pretty darn close until we got to the tips. Now I did not make the tips perfect. I think I have a little bit of error out there, so I'm not too surprised that we are falling off. Unfortunately, this is going the wrong direction. This is going the same direction that the triangular wing does. So the coefficient of lift is increasing as we get to the tip. So to really fly this, we'd have to modify the tips a little bit, maybe cut them off to have the tip so that we will have a decrease in lift coefficient as we get to the tip. We don't want it to increase or the darn thing will stall on us before the rest of the wing does. But for the most part, it is flat, especially at this 1-degree angle of attack. It's flat almost all the way across. It's when you start getting up to the higher angles of attack, this one's the 10-degree, that you start seeing some significant increase in the coefficient of lift. But for the most part, we came close. So I'd say that this program at least comes somewhat close to what we expect, according to Horner. So I think is good enough to go ahead and design our wing. So that will be the next step. Let's go ahead and take a shot at designing our own wing. So that's the next thing to do. Well, I now have a potential planform for the new ultralight, and this is what I've come up with for now. And let me describe a little bit of the features that I like about it. It's kind of halfway between an elliptical and a tapered wing. I'm still using the 2-to-1 taper ratio. Let's come over here and look at it real quick what it is. The root is 4.8 feet, so nearly 5 feet, almost 60 inches. The tip is 2.4 feet. In a minute we'll get into looking at the vortex calculation on what we have for a lift distribution and the coefficient of lift across the span. But real quick, let me tell you what I like about this. I'm giving some thought to having a full span flaps along the back edge. So I wanted to have a trailing edge that wasn't too curved. A little bit of curve's fine, but I didn't want to have significant curve because I'd like to have it be a one-piece flap along the back edge. There is some curve, but that's certainly tolerable. I instead switched the curve to the front edge. And this curve gives us nearly an elliptical distribution. Another thing that I did was I have a 3.3 degree sweep of the 25% chord. The reason I wanted to do that is I wanted the 25% chord of the outer part of the wing to be just a little bit behind 25% chord of the root. If I get the root to stall first before the tip, that means the aerodynamic center of the wing will move aft a little bit. That should cause the nose to tip down and start a stall recovery. Now I have to be careful. I don't want too much sweep in the wing. If I do, then the tip will stall first. And that's certainly a possibility with as much sweep as I've put in this leading edge. But I think I have a solution when we add the flaps in that will help prevent that. In addition, at the moment, I do not have any twist in the wing. We have 0 degree twist out the tip. That may end up changing in the future depending on what happens after I start adding in wing tips and nacelles for the engine and the flaps. But for now we have 0 twist. Let me talk a little bit about how I did this curve. I didn't do it myself. I let this program, OpenVSP, do it for me. What I did is I came out to this blending section. I told it I want to have 0 degrees on this leading edge, 0 degree sweep on both the leading edge and trailing edge. And then I left these corners out here free to be whatever the program wants it to be. And what the program did is it built a curve in here for us. This strength number will cause it to extend out farther before it starts curving. So I played around with these numbers and I ended up with a strength of 1.5 for this leading edge so that it has the curve go out a little bit farther before it comes in. But I reduced the strength on the trailing edge to 1 so that it has a very gentle curve along just about the whole trailing edge. So it's almost straight. Well, let's get to do some analysis on this wing. We get our dimensions and reference lengths from the wing itself, and we launch the launcher. I've added another angle to this calculation. So we go up from 1 degree up to 14 degrees. Now, I just wanted to get a better idea of the behavior up closer to what the maximum coefficient of lift is going to be. This lift almost looks elliptical, so we're close to possibly an elliptical distribution on our lift. As we get up to the higher angle of attack, we do have an odd behavior out at the very tip where it starts increasing left. But for now, I think we're just going to ignore that. It looks like it's behaving reasonably well. Well, let's look what the coefficient of lift is across the wing. It's pretty flat across the wing until it gets out the tips. So this area here looks like an elliptical distribution being flat across here, but then it drops down at the wing tips a little bit like what the rectangular wing does. Up here on the maximum angle of attack that we have here, about 14 degrees, it's decreasing the whole way just a little bit, and then it drops off. I think this is going to work. I think that up here at the larger angle of attack, we will probably have the middle half of the wing will probably stall first, and then it'll progress out toward the tip. So it won't be a stall at the root and then progress out. I think it'll probably be about half the wing stall. I think I can live with that. I think that'll still be a reasonably good stall. I'll get some good buffet, strong buffet. It won't be a gradual onset. Let me know the stall's coming before the stall actually happens and then goes across the wing. I think this will be a reasonable compromise between the elliptical and the square wings and give me reasonable performance. If at some point here in the future, as I'm still doing design on the airplane, I start getting uncomfortable with this flat coefficient of lift across here, I'll just add a little bit of twist to the wing, and that'll bring this down a little more and get me closer to a rectangular performance, rectangular wing performance. But so far I like this. I think we're going to go with it. We've come up with a tentative wing planform for the ultralight airplane. Now we've got to figure out some more parts of the wing, and I believe the next step for that will be figuring out our flaps. So look forward to that video.